Now, the relay scattering is occurs in the blue absorption window between the ultraviolet and infrared absorption tails. Then B, due to the inhomogeneities of a random nature of occurring on a small scale compared with the wavelength of the light. Then C, both A and B, and D, none of these. What is the answer for this? Please type your answer in a chart. Relay scattering that will be occurs in the blue absorption window between the ultraviolet and infrared absorption tails. Then due to inhomogeneity of a random natures occurring on a small scale compared with the wavelength of light. Then C, both A and B, and D, none of the above. Please, all of you type your answer for this. That answer for this, that is about a C, both A and B. Because relay scattering occurs in relay absorption window between the ultraviolet and infrared absorption. Yes, someone has written C, correct, okay. It is about the region here, we have the between the ultraviolet and infrared absorption tail there. And this occurred due to the inhomogeneity of a random nature occurring on a small scale compared with the wavelength of the light. And because of that, a scattering takes place. And that scattering means what? At some particular value of a power, so then your that signal will be scattered, means rays propagating through the fiber that will be scattered. And due to that, the absorption takes place. Next one, the relay scattering can be reduced by the relay scattering can be reduced by A, operating at the smallest wavelength, operating at the smallest wavelength. Then B, operating at the longest wavelength. Then C, both A and B, and D, none of the above. That relay scattering occurs if you see the graph of a relay scattering. So with respect to a wavelength there, and here we have the attenuation or loss. So then you'll see that whether that relay scattering is occur at the smallest window or a longest window there. Okay, so that can be reduced. Relay scattering can be reduced if you have to use the longest wavelength. This one is about relay scattering, and it will be decreasing here. So that's why relay scattering, if you use a longest wavelength, if that is about wavelength, this is about your wavelength here. So if you use the longest wavelength, so then the relay scattering can be reduced. Okay, that is about operating at the longest wavelength. Means above 1300 nanometer, so then that scattering will be reduced. Relay scattering can be reduced there. Next one, the non-perfect cylindrical structure of the waveguide caused by A, irregularities in the core and cladding interface. Then B, core cladding, sorry, core cladding, refractive index difference along the fiber length, then C, diameter fluctuation, then strains and bubbles, and then D, all of the above. D, all of the above here. So the non-perfect cylindrical structure of the waveguide caused by means waveguide means nothing but a fiber. Okay, here in the optical fiber we say that non-cylindrical structure means just like we have a cylindrical structure we say for the fiber, it is about a non-cylindrical, non-perfect cylindrical structure of the optical fiber that will be caused by, that is about a D, all of the above, right? Because irregularities in the core and cladding interface. If that core and cladding interface are irregular, so it is not a cylindrical one, then core cladding refractive index difference along the fiber length means throughout the fiber there is a difference. It is not fixed there. The diameter fluctuations because of the strain. This is about a diameter fluctuation due to the bubbles or a strains there, or that axis is not perfect. Center of the particular core is not perfect. So that's why the there will be a diameter fluctuation. So this is about a non-perfect cylindrical structure. Then next about the relay scattering, not T. Okay, relay scattering occurs in a forward direction. Relay scattering occurs in forward direction. Then B, backward direction. Then C, all the direction. Then D, none of the answer for this. Relay scattering occurs in forward direction or a backward direction because if you see the given particular fiber, a light launches inside the fiber, then a scattering will be occur at some particular portion or some particular point, or it will be scattering occur. So your signal will be scattered. That scattering of a signal will be in all the direction, or in the backward direction, or in the forward direction, or above all the direction. Yes, answer C is correct. It is about the all the direction. Okay, it is in the all the direction. It stimulate that scattering takes place in the relay scattering in the all the direction. But if you consider that is stimulated uh, beryllium scattering and Raman scattering, it is in a forward backward direction and a forward direction likewise. That is about a scattering takes place. So if you see that this Raman scattering means both the direction forward or backward, but in the stimulated beryllium scattering that will be in the backward direction, and you can see that no forward rays are propagating through there. So that's why my question is over now. Okay, and this Raman scattering and backward scattering that I was asking. for you. Next, that no need to go ahead with that question. Okay. Then a stimulated Brillouin scattering and sorry, next question, not answer. This is about the question. Stimulated Raman scattering are not observed in a single mode fiber, multi-mode fiber, both A and B, and none of the above. That is about a scattering, single mode scattering, simulated scattering will occurs in which fiber? It is single mode fiber, multi-mode fiber. Okay, are not observed in. Okay, are not observed in simulated Bernoulli scattering. That will be not observed in the multi-mode fiber, right? It is correct one. Okay, so stimulated Bernoulli scattering not observed in the multi-mode fiber because what is the reason? Because if you see that a single mode fiber and a multi-mode fiber, the core size is small and large. This one is about a single mode fiber, and this one is about a multi-mode fiber. So due to the large core size, that burst, that scattering is not takes place in this multi-mode fiber. But if it is a single mode fiber, the stimulated Bernoulli scattering and Raman scattering both are observed in the single mode fiber because of that core size is small. And why it is not occur in the multimode fiber? Because the core size is large here. Okay. Next question. Optical fiber suffer radiation losses at A, bends on their path, then B, curve on their path, then C, both A and B, and D, none of the above. Answer for this. Okay. Optical fiber suffer radiation losses when we have the bends on their path or curve on their path, or both A and B, or none of the above. That is about the radiation losses. Optical fiber radiation losses. Yes, correct. That answer is correct because we have the curve of the fiber or a bend here and curve both are nothing but the same. So that's why that because of that a radiation occurs. Why? Because that radius will be changes at the curve. So means we can say that it takes a longer path at the curve. So that's why the radiation takes place. So some of the signal can propagate through the cladding layer also. That's why the radiation takes place. Next one, for a single mode fiber, the critical wavelength of radiated light is shorter at the bend radius, which is A increased, then decreased, then no effect on wavelength, then none of the above. What is the answer for this? Here we have a single mode fiber. The critical wavelength of the radiated light, that is about a lambda c, is shorter at the bend radius, which is increased or decreased. Okay, what is the effect? It is about increased. No, it is about a decreased one. Answer is about a decreased one. Okay, it will be a decreased one. Next, the pulse broadening is maximum in, the pulse broadening is maximum in A single mode fiber, then B multi-mode tape index fiber, then a multi-mode graded index fiber, and then D all of the above, all of the above. Now, pulse broadening is maximum in single mode fiber, multi-mode strip index fiber, multi-mode graded index fiber, or all of the above. What is the answer for this? Pulse broadening is maximum in single mode fiber, multi-mode fiber, strip index fiber, multi-mode graded index fiber, or all of the above here. That answer for this, it is about a multi-mode strip index fiber, because that core and cladding layer have the constant difference in the reflected. Now it's, see, it is not correct. Graded index is not correct. To minimize the pulse broadening, we have to use the graded index fiber. Okay. To minimize the pulse broadening, you have to use the graded index fiber. But in that case, if the profile is a parabolic one, alpha is equal to 2, then pulse broadening can be reduced. But multimode fiber, it has a maximum pulse broadening. Multimode strip index fiber, it has a maximum pulse broadening there. Next, the amount of pulse broadening is dependent upon A, the distance the pulse travel, within the fiber, then B, multimode step index fiber, then C, multimode graded index fiber, then D, step index fiber. Answer for this. The amount of pulse broadening is dependent upon the amount pulse broadening is depending upon A, but right, that is about the distance travel within the fiber, because the length of the fiber According to that, a pulse broadening will be increase or a decrease, because a pulse broadening is depend that if you see the unit, so it is per kilometer. Okay, picosecond per kilometer. That is about a pulse broadening. That is about the unit here. The following dispersive mechanism involved in pulse broadening within the various types of fiber. A. Material dispersion. Then B. Waveguide dispersion. C. Intermodal dispersion. And D. All of the above. What is the answer for this question? So dispersive mechanism involved. Meanwhile, you type the answer. I'll write another question. The pulse broadening due to material dispersion can be obtained using A. Group delay. Then B. Scattering. Then C. Material absorption. And D. None of the above. Now here the following dispersive mechanism involved in pulse broadening within the various types of fiber, that is material dispersion, regard dispersion, intermodal dispersion. The answer for it is about all of the dispersion here. Next, the pulse broadening due to a material dispersion can be obtained using the a group delay. Pulse broadening, okay, because it is nothing but a group delay, and that group delay depending upon that what will be the group velocity. So that's why the pulse broadening occur. Then last one, at longer wavelength, the material dispersion is a maximum, then minimum, no changes here, and D, none of the above. What is the answer for this? At longer wavelength, the material dispersion at a longer wavelength. Okay, because if you see that a graph with respect to wavelength and the attenuation here or dispersion, you can say that at a longer wavelength, material dispersion. If you see the graph, it likewise at the longer wavelength, the material dispersion will be a minimum here.